I got that. I think I got it in view.
All right. How are things on campus?
Good. Busy first week of campus, of classes.
How's the first week?
This is the worst you get.
Yeah.
So. Oh, wonderful. Thank you.
Still? Again? Keep signaling me, man.
Wow. You got your people there.
We pay him extra for this. Yeah. He advises me on clothing too, but I didn't take his advice this morning.
You look sharp.
I was hoping for a table to disguise the fact that my pants don't match my jacket. Can't match my jacket.
So which department are you in?
I'm in Mighty. I'm the deputy director of Mighty.
Oh, okay.
Science and technology.
Very good.
Physicist.
I'm at Lincoln Lab, which
Yeah.
has a little bit of overlap with campus, but not that much.
Beaverworks.
We at least have the shuttle, so that's good.
Yeah.
We have Beaverworks. I'm hoping to do a little bit
We
more.
should have a lot more. I mean, often these activities from our project links in so nicely and we didn't know about each other. I think what you're doing is also has a good overlap with what Ignacio is doing
Okay.
because he's also modeling the US grid, right? So there's
Yeah.
a huge amount of overlap.
Increasingly, he and I are working together on developing country sorts of problems, which is
Okay.
taking a lot of what he's been doing in Europe for the last 30 years and trying to embed discrete systems within the larger models. So if we can sort of optimize planning with both at the same time.
Okay. So which parts of the world?
India and Central Africa.
So I
Done some work
introduced
in
you as
Peru.
Professor of Electrical Engineering. I guess
You've
We've done some Peru
bio
too.
for you, but anything else?
So I
you
went
would
down
like
there
me
with
to
John
highlight?
Duffy, who's at UMass Lowell. He used
That's
to be.
fine. I think for this audience, relevant
So we were
things
in
would be
Cajamarca. Cajamarca. So we were working
That's
just
where we were.
relevant things.
south of Lima, a little bit inland.
Yeah, it's
Okay,
like
we
a
were
firm director
north of
RP.
Lima,
Okay, so
in the Parme Valley. So if you could drive about 4 miles north, or 4 hours
But I
north
basically
of
ran
Lima,
all the programs.
take a right, go straight up the mountains to the top of the Andes, about
API.
12,000
So
feet.
part of energy.
Nice and sunny.
Very sunny.
So
Yeah.
basically ran all
Very
power
interesting
electronics and the grid program.
Dynamics there.
That was-
They
I
don't
think
have
that
any
was,
grid at all.
most of the dad's starting to
They require water pumping and irrigation, things like
came
that.
back to MIT and then Rob took
Getting them solar panels takes a lot of energy.
taking some of
Bring
those
a panel
concepts and
to
applying it.
a remote location,
There's
sometimes
Sherpas
on
that
horseback.
we hear from Vladimir's talk.
Sometimes.
Yeah, yeah.
It's not the
Just
type
make
of
sure
things
there's
that
a
you see in the
DOE.
book.
No, indeed. Yeah, right.
API.
Yeah, RP. Yeah, that's right.
Similar situation in Chile, I guess. In a lot of places.
Okay, are we all ready?
Hey, Eugene.
Hey, Rob, how you doing?
I don't know. We'll see.
Try to talk as long as I can, but I don't have that many slides.
Yeah, I think we have
The
plenty
lab.
of time, but generally it's good always on that. Okay, let's get started with the next session, please. Okay, good afternoon. My name is Christoph Reinhardt. I'm an associate professor in building technology in the Department of Architecture at MIT. And Rob Stoner and I have put together this next session on solar deployment. And just some personal words. I think so far the event has been really fantastic. Thank you, Frank and Bob, for putting this together. It's one of these moments where you see all these nuggets at MIT that we are not aware of that happening. So I think this is really successful as a community building exercise. And then at the same time, I always wonder myself, what can I contribute to that after these great contributions? So what we are trying now is basically starting with solar deployment. So take you on a journey really on how get solar cells onto rooftops or into green fields and what makes sense. So we're starting off with some thoughts about individual building owners and their perspective of using solar in their daily lives. And then we are changing perspective again from grid operators. How do you match changing load profiles with new energy supply systems in an existing energy market such as in the US? And then suddenly we switch over, go into areas where there is no electric grid, and how do you then set up best an effective energy supply systems? So as speakers today, we have Eric Morgan, who is a staff scientist at Lincoln Laboratory. Afterwards, we have Rob Stoner, who is the deputy director at MITI for, just get it right, Science and Technology, and is also the director of the Tata Center for Technology and Design here at MIT. And finally, we have Rajiv Ram, who is a professor of electrical engineering and who has worked with Rob over the last couple of years on basically developing technical solution and modeling for microgrid systems in developing countries. So the setup of the panel will be similar as before. We have a series of presentations by the four of us in the order in which I introduced us, and afterwards we have moderated by Rob some questions, and then we opening up to the audience. So with that, I'm actually introducing myself, going over. I'm the only poor guy who has to do that today. Okay, so let's get started. Yeah, just a quick word, same as some of my colleagues this morning. This is, of course, what I'm going to present in the next couple of minutes, the works of of a whole group at MIT. We are called the Sustainable Design Lab, and historically we've worked on workflows for individual buildings. So how do we help architects making individual buildings more energy efficient? But we are applying now similar technologies and new workflows to what we've done in the past to whole cities and neighborhoods. And of course, part of this equation is always solar photovoltaics as well. So I just wanted to start off after what we heard today with this idea of the individual's perspective. And I just wanted to query the audience a bit. So who grew up or who is living in a house with PV on the roof right now? So there are some of us. So then the next best thing, that's a lot easier, who is purchasing green power? So that's a lot more of us, so individual action. And I would like to get a sense, who thinks that by doing so, does that bias your choices towards more sustainable living? Do you use less energy because you do so, generally? Okay, no, that's interesting. So I think there's a lot of interesting research there which puts the whole question of should we put PV onto personal rooftops or onto the green field. There are, of course, certain advantages, unless you're Rob Stoner, that when you put PV onto a roof, that it changes when you are aware that the electricity that you're generating is right there and it comes from you. I think that creates an awareness and secondary effects when it comes to the overall load profile, the energy that you're using, that we haven't really covered so far within this conference. And along the same lines, I just wanted to pick one of these many cool spin-offs that come out of MIT. There's this company called SOFA that makes this little solar benches here, comes out of MIT and Harvard. So they have this little device that you see on the left-hand side, and if you live in Cambridge, you can try it. You can take your smartphone and plug it in there and charge it while you're sitting in the park. And of course, when we look at the big question of energy supply and demand, this is a really small gesture, but I think it really does a lot to how we think and relate to it. And of course, once you are thinking about areas where there is no electric grid and everybody being dependent, if you're a migrant coming from Syria through Europe, having PV and having your smartphone all the time charged up is really key. So these small little things still can make a big difference. And then I thought this is really an event like for the MIT community. So if you are a student at MIT and right now you are involved in a spin-off and now the spin-off was successful, what's your first big dream as an individual? Well, maybe you want to buy a car, right? And then when you have now the means available, you might buy a Tesla. And that's, of course, pretty simple. If you have the money, you just write them a check and you get the car back, right? And then the next step as an individual, you might want to say, well, I want to match that with a great house with a great PV system on top of it. And buying the house is relatively simple, again, if you have the money, but then it becomes, we learned that it's very difficult, right, to finally get this PV system on your roof. So you might ask yourself questions, well, is my house any good for solar? And this is just some technology that's getting more and more traction that we started developing a couple of years ago at MIT, is create this very detailed individual owner maps. So here's a map of the campus. We can use nowadays big data, LiDAR data, convert that into three-dimensional models of a whole city. Then we can calculate for every square foot of roof area in a city for every hour of the year the solar radiation. And that converts them in this type of information, such as this app here that you see here that allows you basically to type in an address, and then you can draw just with your mouse a PV system on your roof. And then all these things that we talked about that are very complicated for an individual to understand, you get this information. How much does the system cost? How much incentives do I get? How much payback do I have? So really, we are trying to bring here the information at this level, back of the envelope thinking, right to individual owners. So we would pay for a solar system $3,000. Right now, because the subsidies are so high, as has been pointed out, right now, within 6 years, the system paid for itself, and then it would cover a third of our electricity bill. So the advantage here by this type of technology, making it available on a very large scale, that individual owners can actually, that's a call to action, right? So how does this scale up? If you just take some cumulative data for the solar map of New York City, for example, you get these enormous numbers, right? In terms of potential, we already heard this morning. Well, you could create 11 gigawatt hours of electricity per year, $40 billion in local business. So you can create renewable energy for 1.2 million American homes if you pick the high-yield solar rooftops. So this kind of information shows you the potential is there and where exactly it exists. So do this type of technologies actually help you? There we did a little case study that was mapped well, working together with the Audubon Society in a little place on Cape Cod called Wellfleet. And there, basically, they started a SolarWise program, went from house to house, trying to convince people this is really a good idea. And this is the kind of results that you get. So within 3 months, 10% of all households went solar there. And the reason for that is really that people on both sides, installers and homeowners, used the map, and you basically had informed users, informed installers, and you came together very quickly. So this really shows you that in terms of how the financing thing is working right now, we could have a big change, having a lot of penetration of PV very quickly in this country. So we already heard pretty much all day how the operators feel about that. That would be disastrous if the same thing that happened in Wellfleet would happen today in Manhattan as well. So another component of what we are trying to understand is really how do we develop integrated systems that are looking both at the demand load curves of buildings as well as the supply side. So in order to do this, we are using Boston as a case study. We're working with the Boston Redevelopment Authority directly with funding from the Massachusetts Clean Energy Center, where we are generating basically energy models for 100,000 buildings in Boston, hourly load profiles. And then, and Eric Morgan is going to talk about this, we are matching this predicted load profiles with various microgrid and other energy supply scenarios. And by getting there, we really want to go towards this more integrated part because, of course, we know already how load curves look like. So I show you something here that's very similar. So maybe 30 seconds, how do you actually model a city? So if you want to model a whole city, use GIS data and various techniques to build kind of 2.5-dimensional models of a whole city, and then you build your building into archetypes. You then, and that's the biggest part of this work, you are creating a database with typical energy users and building stock information for your whole building stock. And then you run the simulation. And this is how something like this looks like. This is just some brand new results that we did last night for the Back Bay. So you see here in Back Bay the energy use per hour of the day on the hottest day of the year. So obviously you have a lot of small residential buildings and some bigger commercial buildings, including Prudential Center there. And then if you go just through the day, you obviously see a lot of energy use coming on. You're reaching the peak pretty much in the afternoon, and then it drops off. So the curve that you see on the left-hand side basically tells you the electricity load curve simulated for Back Bay. And then in yellow, you see various supply scenarios for PV. So we have the same curve that you've seen before, right? The peak for the buildings is actually later within the day. But now we really created these curves from the base physical principles up. So now you can use this and say, what are various ways to change the load profile? So what type of buildings should I trigger in an area, and what kind of changes should I do to this building? We make them tighter and so forth. And this is really something that we have to look in more when we want to meet this. How do we change the demand at its origin? So with that, I wanted to switch over to Eric, who's going to tell us what else you can do with this type of load data. Thank you.
Thanks. All right, thank you, Christoph, for the introduction. And so I'm from Lincoln Laboratory, which is a branch of MIT that is in Lexington, Mass. And I'm limited a little bit about what I can put on the slides here, so I apologize for that. This is going to be a little short in terms of slides, but I hope longer in terms of what I actually say. So we have been working with campus and Christoph in particular on trying to figure out and understand how Boston itself works in terms of the energy building profiles, et cetera. But I wanted to give an overall sense of what the United States electrical grid looks like right now. And so it's basically three things: generation, transmission, and distribution. Generation is huge, typically huge plants like coal plants, nuclear plants, natural gas plants. And then it goes to transmission, which is in the hundreds of kilovolts, and then down to distribution. So we start at high voltage and then drop down. So once we get to a place like Boston and we start to go out into the different buildings, we're at lower voltages, and that's where we have substations in it, et cetera. So a couple of numbers on generation. For California, yesterday at 1 p.m., solar power was 12% of their 42 gigawatts. For the entire day, for the energy, it was about 3.5%. Today in New England, natural gas was 60%, nuclear was 25%, solar was 0.06%. And that's, you can see outside, that's probably why, because there's a lot of clouds. So we have a lot of work to do trying to bring PV online, get it into Boston and other places in the state and around New England, and get it onto the distribution part of the grid, and maybe into the generation side of the grid. So when you're on the distribution side, that's basically behind the substation. So now from the left-hand side, you've got high voltage coming into the substation. Substation takes that down and brings it into the communities. And so that's where you have the opportunity to put in things like CHP plants, that's combined heat and power, where you're running a small turbine. A building like this might be running something like 1 megawatt at peak. And so you could match a CHP plant in the basement with the loads here. You could also put a solar array on the roof. I'm not sure if this building actually has one, but it might. And then you could imagine coupling the output from the PV to the output of the CHP and combining that into a localized grid, which would be just this building. So when you do something like that, you essentially detach from the grid at large, the transmission and generation systems that you have elsewhere. So you've got, like there's 4 nuclear plants, you wouldn't be able to see those. You wouldn't be able to see the coal plants or the natural gas plants that are in New England. And so that's what we call a microgrid. And a microgrid is kind of what Boston wants to do moving forward to the next 50 years or so. A 50-year plan is to get microgrids employed in certain areas of Boston, certain buildings in Boston, and reach critical loads where you have hospitals like Mass General, residential areas where you might want to put a lot of solar, because residential areas, if you look at the maps, are very large but don't have a lot of huge loads. So that's a good spot for a large PV to be on all the roofs. And then, obviously, if you're going to have a lot of PV, you're going to have to put some storage in there. So we're looking at Lincoln Lab at how you would couple all of these things together behind the substations and not necessarily on the transmission side. And you can see this load profile here on the bottom. Because we're a federally funded R&D center and we're looking at national security issues, we do look at critical demand. So that is, how resilient can your grid be? If you have a Hurricane Sandy-like event, what do you do to make your grid stay online that whole time? And one of the things that we found is microgrids. And certainly places like Goldman Sachs and Manhattan did not go down when Sandy came through because they had a microgrid. And so, like I mentioned, Boston is now at the forefront of microgrid development. They are looking at CHP. They're investing millions and millions of dollars into studies like the one we're doing with Christoph, trying to put CHP plants in PV plants in certain districts. This is the Seaport region, which has some actually fairly interesting loads because there's a lot of cooling of fish and other commodities. And then there's also large buildings. So in this type of region, you might pick a CHP plant and then have solar on the roof. But if you go out to Hyde Park or Mattapan, where you don't have huge buildings, then you might want to pick more PV. But there seems to be some political desire to get this done. And so the mayor is, I think, going to be at a conference in 3 weeks or so and going to be listening to all the reports about how to actually employ this in Boston. And so what we're doing at Lincoln Lab is we're going to actually make a microgrid at Lincoln Lab. And that's kind of the situation on the left where we're going to develop these integration technologies. So we're going to actually have an 850 kilowatt PV plant on our parking garage. We're going to integrate that with some diesel gen sets, some battery power, and we're going to try to island or microgrid one of our buildings on our campus. And so that's going to try to inform kind of the later designs in Boston itself, how you would do this on a building level, how you would do this building, how you would do maybe certain residences. And once you do that, how do you get a community like, for example, Back Bay, like Christoph showed? How would you get the Prudential Center to be an anchor building, and how do you get PV to kind of cover the smaller buildings in the surrounding area? And then how do you marry all of that technology together as one cohesive grid? And then once you go to that scale, then you could imagine going to a larger scale in terms of all of Massachusetts and putting those microgrids in certain areas that are advantageous for not only criticality for national security, but also things that just make sense for maybe CO2 emissions. And so that's something that we're looking at Lincoln Lab. And I think I'll stop there. I think that's all I had. I won't go into those, but I am available for discussion later. I can say a lot more than I can show, let's put it that way. So, thank you.
Well, thank you. Let me just say at the outset, I'm going to go without slides. I was reminded as I was trying to prepare some slides of a remark that John Deutsch once made after watching one of my presentations. He said that people who lack an aesthetic sense should try not to use PowerPoint. And how bad can I be? Is the question. I'm talking about the role of solar in developing countries, as I see it. And so let me just frame the situation for you very briefly. I think someone this morning mentioned that something like 1.5 billion people completely lack access to electricity. Probably something more like twice as many feel like they lack access to electricity. They don't have regular electricity or enough electricity to do things like run dishwashers and microwaves like we do. So the world is pretty different outside the United States, Europe, and parts of South America than it is here. Most of those people live in South Asia and in Sub-Saharan Africa. By the middle of the century, as the rest of the world becomes electrified, most of the people who don't have electricity will live in Sub-Saharan Africa. And there will be more people living in Sub-Saharan Africa without electricity by 2030, 2035 than there are now as a result of population growth, at least according to the IEA. The second point, I guess further, is that most of those people will be in rural areas. The world is rapidly urbanizing, but urbanizing slower in sub-Saharan Africa than elsewhere. A second sort of element of the frame is that coal is the predominant source of electricity in most developing countries. We all know about that in China, we know about it in India, it's happening elsewhere, and the use of coal is tending to expand with very serious consequences for local environments and obviously also for global climate change. So that's kind of the frame. And I'd like to make 3 points on top of that. Most developing countries recognize the possibility that solar power can be very, very important to them as they expand their electrical systems, but it's hard. The second point is that off-grid applications of solar can be very important in expanding access rapidly, at least for an interim period in most developing countries. And the third is that ultimately those technologies will likely, in my opinion, but I think it's supported by the numbers that we've been developing, will be subsumed into expanding public grids. So let me come back to talking about this coal situation. India currently has something like 300 gigawatts of total generating capacity at any given time. And Prime Minister Modi has announced recently his intention or his desire to double the consumption of coal, actually double the production of domestic coal, which roughly correlates with doubling consumption of coal in India within the next 5 years. That's a big deal. At the same time, he has announced that they will quintuple their target in India for solar power from 20 gigawatts to 100 gigawatts, roughly a third, at least in nameplate terms, of the total generating capacity of the country. That will translate, if it's done, into something like 10% of the electricity produced in the country. There are a lot of reasons why it's not going to happen. India, like all developing countries, has an imperative to expand its system, expand access, and to do so at the lowest possible cost. And PV is not yet the lowest possible cost. Moreover, it's difficult in India to integrate solar through rooftop installations than it is in our country. Roofs are more complicated there, but also with urbanization and pressure on land, people are tending to end up in apartment buildings, really tall ones, superblock types of the sort that are going up and have gone up in China. And you'll see them all over the place in India if you travel there. Fourth, with the imperative to expand access, the requirement with the deployment of intermittent renewables within the system to reinforce lines to enable power reversals and so on, which is a cost, takes second place to the creation of further distribution lines and more generating capacity. And so it's even harder there than it is here. And I guess as a fourth point, Dick Schmalazy pointed out in his very early remarks that much of the solar that's being deployed in this country is only feasible because of the very large number of subsidies. And even at the much lower level of deployment than Prime Minister Modi envisages for India, it's already causing a strain on utility providers. These problems are multiplied in India, and so it becomes even more challenging. I could say similar things about Indonesia, Malaysia, and other South Asian countries, but there's some rays of hope out there. If you go to countries in sub-Saharan Africa where there's a lot of hydro potential and a lot of existing hydro capacity, and Kenya is a good example, adopting solar on the grid as a displacement technology that can displace diesel, which is widely used in developing countries. It's easy to get one's hands on and to import. It's easy to add diesel capacity in relatively small amounts to the generating system and so on. But solar can be deployed to displace that diesel and reduce the overall cost of power generation provided that two things are true. One, you have some way to absorb through the course of the day the fluctuations in power that come from solar, the smooth fluctuations, as well as the more rapid ones that come with climate, or rather with clouds, and also that the grid can handle it technically. We did a little study to look at Kenya in particular, and determined that you can displace essentially all of the diesel in Kenya with something like 100% nameplate capacity, 100% match to the existing hydro capacity. And the effect on electricity prices is a reduction of something between 20 and 0%. And so it's attractive economically today to do this in Kenya. So it's important for these countries to understand these options, and we've been trying to get the word out and help them with their planning. But let me return to off-grid access and expanding access using solar. I raised my hand to say that I do have a house that has solar power at the beginning of Christoph's remarks, but I also didn't raise my hand when he said, does that drive me to be more energy efficient? And the reason is that my house is off-grid. So I don't have anyone to sell my power to. So everything I generate, I use. And unfortunately, because my house is an off-grid weekend house, I only get to use something like a quarter of everything I generate. So I figure my generation would cost me about $1 a kilowatt hour if I used everything I generate. But since I'm only there on the weekends, it's about $4 a kilowatt hour. So I bring my laundry down there, I run the microwave all weekend, I vacuum, just trying to drive my costs down. So I've thought about these stupid systems. And you know, you don't have to have as big a system as me. I sized mine to work great in December, and it's ridiculous in July, to still feel a little bit electrified. And so solar home systems have long been deployed in many developing countries as a way of getting some sort of minimal home-like access. You can't have a dishwasher or a microwave, but you can run lights. You can play your radio and charge phones and so on. But it's still a sort of expensive approach. Solar home systems are always sort of semi-customized. They have to be installed by somebody, they have to be maintained by somebody. And so there's been a relatively low level of adoption of these things around the world. But over the last 5 or 6 years, small appliances have begun to appear that don't need to be installed, that you can buy in a store, that can be manufactured in very large volume using parts that are procured in very large volume, usually in China. And these things can be brought home, and they range in price anywhere from sort of $10, which would get you a lantern that contains a battery and a little LED fixture and a light, a solar panel and a charger, and that would provide you with enough electricity to run that light, and easily could be recovered over a period of a couple of months versus the cost of buying kerosene and burning that instead. So it's attractive financially. And these things have begun to take off, and very large numbers are now deployed in many countries. But that economy of scale of manufacturing also enables more sophisticated things to be deployed. And so what's happened increasingly in Sub-Saharan Africa is that more sophisticated things than mere lanterns have begun to appear, and they've begun to compete with solar home systems. So these are solar power and lighting products, so-called, that have light bulbs, but also solar home chargers. Sometimes they have a USB plug-in that could be used to run a 3G modem so that you could have internet. Many of them will have plug-in lights that you can use to expand them and then run wires throughout your home. They may cost anywhere from $100 to $300, but you get a lot more for your dollar than you do with a solar home system. These things are expanding in sales and have done so for several years now at a rate of between 40 and 80% compounded annually. So they're having a big impact. The potential market is in the hundreds of millions of people, and that is a positive thing and enabled solely by solar. The economies of scale that comes with that manufacturing can also appear in a different form, and that is in in small grids that are not connected to the main grid. And I'm talking about microgrids, but in a very different sense that Eric was talking about them. Microgrids that aggregate what would otherwise be solar home components, the batteries and the PV panels and so on, at a central point where they can be maintained less expensively, but also they can be procured in larger sizes, and so they're less expensive on a per unit basis. That's traded off against the cost of providing wires to connect homes within the community to that central station, but in many cases that cost can be low compared to the economies of scale that are gained by this aggregation. And so the idea of solar-powered microgrids has taken hold in many communities. And Ignacio Prezariaga, who spoke on the previous panel, and I have begun to investigate this. And we're building a couple of solar-powered microgrids in India and hope to build another one in Rwanda. We think that these can become a very important part of the energy system in many developing countries, especially sunny ones, but they don't have to be astonishingly sunny for the economics to work out. However, and this will be my last point, these systems provide electricity at a cost that is almost unavoidably higher than the cost of providing power from a centralized grid, even using the same technology. There are situations where that's not true, when, for example, a community is very isolated and would otherwise have to be supplied with its own power plant of some other type. But when demand reaches a certain level and the cost of providing those wires and additional service is paid for by consumers buying electricity, the grid tends to win out. So our vision of the future in many developing countries is that microgrids, solar-powered microgrids in particular, as well as hydro-powered microgrids, may play a very important interim role in expanding electricity access that feels more modern than one would get from a solar appliance, for example, but will ultimately be subsumed by expanding public grids over the ensuing 30 or 40 years. But we think there's a period of several decades where they'll matter. So I'll end it there. Thank you.
All right, thanks. So I'm going to be illustrating some of the points that Rob discussed, because I actually have PowerPoint slides, and we actually have some non-trivial overlap here. So just a quick overview. So I'm going to primarily talk about the India context and the work that we've been doing, supported by the Tata Center, to be able to generate a more intelligent, lower cost microgrid that we can deploy. And just a little bit of the operating context. So this is giving you a sense of the per capita energy usage in India. And the number looks quite small. Pakistan is also quite relevant, so is Bangladesh. And of course, this is small for all the wrong reasons. It's small because the quality of electricity service for the billion people that live there is actually quite poor. And so just to kind of reinforce the points that Rob made, about 80% of the villages have at least one electricity line, but about half the rural households don't have electricity. There are in excess of about 300 million people in India who don't have access to electricity. Just illustrating for you the points that Rob made. And so there's a critical need to be able to provide electricity access. And you can actually argue that there's a moral need to be able to deliver this service as quickly as we can. And yet we have to balance that with the recognition that India primarily generates electricity from coal. And as Rob said, if we look at the business as usual projections, we're looking at more than a doubling of the increase in generating capacity of coal. And so we've got to balance the moral obligation that we have to provide that 300 million people with access to electricity to improve their quality of life, with the practical reality of basically bringing on all of this fossil power fuel plants and the CO2 generation that goes along with that. So remembering that India's population is quite a bit larger than the U.S., that 275 gigawatts of peak generating capacity as of last month, that's about a quarter of the generating capacity in the United States. And we're talking about a population that's considerably larger. So the concern that I have is if we focus primarily just on meeting our moral obligation to provide technologies to do the grid connection, we risk basically moving this 300 million people from just basically not being connected to the grid, but being connected unreliably, being connected by dirty resources, primarily coal. And that has a whole host of other consequences. So I think the question that we have to ask, how can some of the technologies that we've been talking about in the previous sessions play a role in the context of bringing renewable energy to India? And in this case, we really can't wait till 2020. We can't wait till 2030 or 2040. Some of the projections that we saw for when storage technologies will be cost competitive, when we're going to hit the $100 per kilowatt hour target that actually makes storage something that's widely done in the United States for doing renewable support. We really can't wait for that, because by that point, the grid extension will have actually reached these 300 million people. The coal-fired power plants and the gas-fired power plants will have been turned on. And then we're going to be asking the question of, like, we're going to be displacing all this brand new asset that just got turned in. Just to give you another element of what makes this challenging for India, just to give you a sense of the electricity tariffs. So if we look at commercial industrial tariffs, they're well subsidized, and they tend to be sort of comparable to what you would pay in the United States for electricity. But in the agricultural sector, for quite a few decades, farmers have been used to basically getting electricity for free. Now, of course, that electricity that you get exactly what you pay for. So a lot of the farms that we work with, they basically get electricity for 2 hours a day. In the middle of the day, they don't pay anything for it. They have very poor opinion of the state utility boards that basically grant them that electricity access, and are very skeptical, actually more skeptical than the people who've never had electricity, about electricity service and what it can basically do for the quality of life that they have. And yet, unfortunately, these state utility boards have convinced them that something like electricity basically should be free. And so these are the people we have to convince to basically start paying for electricity, right? To basically pay for the microgrids, to pay for the photovoltaics. Now, even if you live in New Delhi, where you have electricity in principle at 24/7, but of course you've got blackouts that occur on a regular basis, you're likely to basically take into your own hands the hardening of your power. And so if you're a middle-class household, you're likely to have batteries and solar inverters that basically make sure that a few of the lights in your household are on all the time. And what that does is it actually increases the cost of electricity for you. So that requirement of actually needing to have a battery and some power electronics, every household in India, again, Chinese-made components, basically increases the tariff by 17 to 79%. So it's a considerable actual increase in your effective cost of electricity. So within this context, right, where batteries are expensive, inverters are expensive, photovoltaics are challenging, people are used to paying essentially zero tariff in large fractions of the country, we kind of add to that the challenges of just doing photovoltaic integration. So in the previous session, we had a lot of discussion about the intermittency of solar and the challenges of doing solar integration in the United States, where people are willing to pay for that. And of course, there is this if you actually look from the bulk transmission provider, as was mentioned in the previous panel session, and people from the transmission side kind of look at photovoltaics as sort of the worst case scenario, right? You basically are getting rid of the system inertia, so you have to basically do control decisions much more rapidly, and you're getting rid of the governor control. So the primary thing that you're used to controlling on the conventional grid is basically lost. So in the United States, we're kind of looking for some other asset to control. And that asset, we had a lot of discussion of solar, of batteries as being that alternate asset that we balance when we lose our ability to control the governor. That asset could be demand response, right? That's another popular example. So when we're thinking about basically kind of rolling out photovoltaics and kind of bridging the gap between that 275 gigawatts and the 1,000 gigawatts or more that India might expect to have with solar, we've got to think a little harder about how we plan to do that. And what is it that we're going to control when we basically can't expect there to be low-cost storage in a timely fashion to come on. Now, these are real issues even in the US, so I think this is kind of a timely illustration. So Hawaii, is a microgrid, and they've got a high penetration of renewables. And just in terms of, just to reinforce that this is a problem that we're facing even in the United States. I mean, I think the idea that the bulk transmission grid can basically handle 50–80% renewables kind of makes a lot of assumptions in terms of how we basically tend to do control and how much actual curtailment that we have. But if we want to, even in the context of Hawaii, where we actually pay very high tariffs, the grid there is basically considered saturated. The inability of the Hawaii grid to be able to kind of manage the intermittency of solar and do it even at the tariffs that they're paying locally has made it so the governor has basically put a stop to photovoltaic installations. So, this is something that we have to keep in the back of our mind if we're thinking about building microgrids that are going to be using photovoltaics and actually doing this cheaply enough to be able to roll out in the developing world. And then just to kind of reinforce that again, so in the context of US, if I look at PJM, which is the largest of the RTOs, represents about a fifth of US electricity delivery. If you do 50% generation of renewables, you're talking about curtailment of the variable energy is about 21%. So I don't think we can afford to basically just throw away 1/5 of all the energy we generate from these renewable assets. That actually adds a non-trivial amount to the cost of the electricity. Now, of course, like having other things to control, like storage, can help you with that curtailment. Having other things to control, like demand response, can help. So, so let me basically now switch again back to the India context. So, we'd love to have a microgrid. So here's an example of a company called Marigaon. It's one of those companies that's actually whose market is actually growing quite rapidly. What they do is they contract with an entire village, install a 280-watt solar panel, and what they do is they provide, they're not selling you kilowatt hours of electricity, what they're selling you is a service. They're selling you lighting for a certain number of hours and cell phone charging. And for that, they're able to charge you more. Now, of course, obviously, I'm missing an important part of this. Like, all they did was basically build a solar panel and then basically light and run wires to lighting. That would be a very ineffective microgrid, right? Because you'd only be able to turn the lights on during the day. And so a critical part of what they do is actually have a battery bank that does storage. And so they expect all the loads that they serve are loads that are primarily going to be on at nighttime. And so they need to be able to store all the energy that they're going to serve for that day has to be stored in the battery bank, kind of like Rob's house, right? And so if we kind of look at the capital cost, we're talking about a system that has a peak generating capacity, a nameplate capacity of 280 watts. So in practice, probably less than on the order of 100 watts. That costs about $1,000, right? So that's several times the tariff that we pay in the United States. So that 50 cents a kilowatt hour to $1 per kilowatt hour that Marigaon charges, I mean, it's better than nothing. Thousands of villages have signed up to basically get this level of service, even though they know that all they get is 10 watts of electrical service going to their house. It's enough to basically give them lighting and cell phone charging. They can never basically hook up a television set. They can never have a refrigerator. It basically requires them to basically build another entire infrastructure to support that. But you have to the thing to realize is that there's basically been some political blowback about this, right? The fact that the electricity tariffs are so high, even though they're providing these services, there's this sensitivity very similar to what was happening in the microfinance world, right? Where interest rates are high, but it was the only place you're going to get a loan. Well, this might be the only way for you to get electricity, but if the tariffs are this high, there are some serious concerns, right? There's serious concerns that these companies are basically gouging these local villages, even though I don't think that that's what's happening here. But you basically have, so what that says is you have to basically deliver low-cost electricity in this microgrid context and do it in a way, and do it in some way using a set of technologies that have yet to be invented. So I think if I look at the lessons that we've learned, so the grid itself basically lacks the funding to provide universal access to electricity today in India, right? I mean, we can basically kind of dream all we want about connecting these 300 million people to the wires, but we don't have the generating capacity in place. We also have decades of history that basically says just doing grid extension in India doesn't mean you basically guarantee quality of service, right? We've got hundreds of millions of people that basically have wires that are basically officially connected to the grid, but have 1 to 2 hours of electricity service and utilize that service quite poorly. If we look at individual solar home systems, there are about 1.2 million solar home systems, like Rob has mentioned, unconnected to the grid, just a solar panel and lighting and battery. They're difficult to finance because you're just on your own to try to go out and finance them. And they're challenging to extend. To basically make it so that you can run appliances that can actually enhance your productivity beyond lighting is actually quite challenging. So microgrids, again, in the case of Marigaon, they require an entire village, 30 people to get together and make a uniform decision to go ahead and basically install the microgrid. So it requires a fairly rigorous planning process, and it's actually labor intensive. Like the way that the payment processes work actually requires someone to go out and basically collect tariffs. So the model that we came up with was what we call Ulink, and we've been working on this for about 2 years now. And so the idea here is we take one of those solar home systems, and in that solar home system, we basically put a larger panel, like a panel that's large enough for you to be able to run the loads that you locally have. But we kind of recognize that these solar home systems actually leave some money on the table. There's some excess capacity that's in the battery, and there's excess generating capacity during the day that's not utilized. And so the thought is, like, can we basically make it so that there's an easy way for the owner of that generating asset to basically turn into a micro-utility, to be able to sell that excess generating capacity that they have that when the sun is shining, or the excess energy that's basically stored in their battery at the end of the day to their neighbor. If there's a way to basically do that, you can imagine that the neighbor doesn't have to pay for the PV panel, the battery. All they have to pay for is the interconnection. And now all of a sudden, it's a model that looks a little bit more like a cell phone. You're basically paying for the appliance that connects you to a network, as opposed to basically having to generate the infrastructure all from scratch. It also takes advantage of a couple of important things. One of the things that we know is that even if you're living in a village that has no electricity connection, the likelihood that you have cell phones is very high. So we spent some time over the summer in a village that had never had electricity, but there are a few households that had 5 cell phones. So they had 5 cell phones because somebody's job to go once a week to charge the phones, and it was they basically had to charge all 5 phones. Came back, they would use one phone, and when that died, they used the next phone, and it died. They used the next phone, and it died. And so the idea is that you've got a connection to a market and a communication infrastructure that you can leverage for electronic payments. Now, this is something that's basically what's widespread in Africa. Is actually starting to come up in India, and the idea is to be able to, if you're building a grid from scratch. Kind of building these kind of e-commerce capabilities right from scratch actually makes a lot of sense. Then, of course, you can actually build this kind of grid. We're trying to design it in a way that you can build this in an ad hoc sense. So there doesn't have to be pre-planning to figure out which loads are actually connected, which homes are connected. But on an available basis, you can basically, if you own the generating asset, you can basically sell electricity service to your neighbors. And you can keep expanding from that. The boxes that we have that are actually connected to the generating unit that manage the battery, they automatically provision the electricity using a kind of an agent-based system to be able to figure out which loads to basically serve at a given units of time. And the key thing is that as you keep expanding the system, you can actually take advantage of the fact that one of the neighbors who was buying electricity now wants to be he has his own generating asset, and he wants to basically contribute that to the overall grid. And so these are actually all the power converters that are actually located at the generator are all bidirectional, so they can basically absorb power from neighbors as well. And so the idea for this is to basically realize scale, because the hardware itself, we've tried working very hard to basically make it relatively low cost, and I'll share some of those numbers with you. We try to incentivize the generators because they actually have something to sell by virtue of actually buying this. Not only are they improving their own quality of life, not only they're increasing their own productivity, but they actually have a specific asset, an energy asset that they can sell to their neighbors. If we kind of look at a little bit what the box looks like, the box actually is black, the real box, and so it looks something like this. So there's actually a plug that goes in to the generator. So from the generator's household, you had a wire that basically plugs into this box, and that box basically does all the home energy management. It monitors your energy consumption, basically interacts in terms of the market, so it actually keeps track of all the prices and payments, but also it actually has outlets, so you can actually plug appliances in there. Very different from any of the microgrid solutions that we know about in the sense that it supports pluggable loads. Now, one of the key things here is that once you start, as you start to expand the system, there's a couple of interesting ways to kind of try to drive the cost out of this. Driving the cost out of the PV panel, it's considerably cheaper for a solar home system to basically have one large 280-watt panels than basically giving everybody a small 60-watt panel. So there's an economy of scale with the photovoltaics. Now, the batteries don't realize that same economy of scale, except for in two kind of important ways. One of those important ways is not everybody is utilizing their load simultaneously. And in fact, the electronics prevents them from being able to do exactly that. And so you can actually reduce your peak demand and actually kind of resize your battery as a function of that. The other thing is that we've realized that once you're starting here from people who don't have access to electricity, once you've given everyone about 20 watts of electricity to be able to run their lighting and run their cell phone charging, the next most important loads that they want to run are loads that are daytime loads. For example, in the villages that we've been working in, they want to have fans. So when they come in for their 2-hour break from farming in the fields, they want to have a fan to basically cool themselves off as they take their afternoon nap. That's a huge load compared to a light bulb, and it's a daylight load. It doesn't require you to increase the size of your battery. What it requires is basically having a slightly larger panel. So it's a much cheaper load to serve. A lot of the other, like the third load that you might have, are actually like all productivity-oriented loads that you expect to run in the daytime. That you can actually, on a best effort basis, you can use the peak generating capacity of your PV panel as opposed to kind of demanding that you have extra storage on your battery. So there are techniques like that you can use to kind of basically drive the cost out of these systems. So in terms of what is our cost target, so we're kind of looking that if you own the generating unit, we basically want the PV panel, the battery, and the box, the power electronics that actually manages this autonomous grid for you, to basically cost as much as today's solar home systems, like comparable to those 1.2 million systems that are out there in India for 15 to 20,000 rupees. And the box that you basically buy, so if you can't afford to basically buy your own PV panel and battery, and all you want is basically some connection to this sort of microgrid that's basically been growing up organically, that box we're targeting for about 1,500 to 2,000 rupees. Now, these are incredibly low numbers, right? So if you kind of, it's something like $10, $20, right? So the reason we came up with these numbers are the kind of cost of a cell phone, but these are also above the bill of materials for what we've already been building out for our demos. So these are numbers that we know we can hit because we've actually started to do demonstrations. We've done a field trial in July. We've actually hit our bill of materials costs for both the generating box as well as the supply box. And we're kind of hoping to basically get the control infrastructure sufficiently robust that this can actually grow in a completely ad hoc way. So yeah, with that, I'll stop. Thanks.
So I'm taking over the microphone now. I don't know if I'm on, or am I on? Am I on? I'll just shout. So Rajiv, you've tossed out some pretty big ideas there in the guise of rural electrification in India. And you've got this completely ad hoc system. There's no operator. Yep. You've got a sort of feed-in tariff concept. You've got load shedding. You've got demand management. You've got time of day pricing. Yeah. Are you trying to tell us something about the future of our grid? Is there a translation there?
Well, I mean, so I think a lot of where these ideas came from was sort of a frustration of how to basically how to get renewable integration to work in the U.S. And I think one of the challenges are that there are you basically one thing that makes renewables integration very challenging here is because we lose system inertia as we replace classical generators with photovoltaics, right? So all of a sudden we need fast response. But fast response is actually not compatible with a lot of the reserve that we have, the reserve capacity that we have existing on the grid today. And so you basically are challenged with how do you find things that are reactive controls that you can put on the existing electricity grid. Demand response is a great example, but the U.S. electricity grid isn't designed to be fully observable, so there isn't good communication over all assets that you might want to control. In this case, since we're basically building a grid from the scratch, we're basically making it so that all the assets communicate with each other in a guaranteed way. We use very, very low-cost twisted pair communication to do that. So while we're running power lines, we're also just running very cheap twisted pair communications. That actually resolves one of the big challenges of actually doing controls in the U.S. I think in the U.S. we're kind of we're living in a world where we're kind of imagining high penetration of renewables, and in the places where we have high penetration, that's where we already have large storage capacity like hydro. Here we're trying to drive the price out of storage, kind of, because if I basically have to wait for Yetming to basically deliver me a lithium sulfur battery at $100 a kilowatt hour, I'm worried that basically the Modi government will basically be done with their grid extension program and will have delivered essentially free electricity for 2 hours a day using coal-fired power plants to the rest of India. And that's something that's not acceptable to me. But I think a lot of these ideas of doing autonomous reactive controls, distributed controls, are things that the U.S. is really interested in. I know ARPA-E has a program called NODES, and the NODES program is actually using a lot of these ideas in the context of the U.S. electricity grid, in the context of smart buildings and building integration, building energy management systems that actually play well with the electricity grid. If you kind of think of it, we're basically doing exactly that, but we are doing it at the level of individual loads, small households, and kind of using those kind of controls.
Mm-hmm. So Christoph, maybe I can turn to you. I want to try to leave at least 10 minutes for the audience to ask questions as well. So please think of your questions while we're going here. We'll give you about 3 more minutes. We're talking about kind of untidy systems on this side of the table, and you're talking about rather tidy systems on your side of the table. And I wonder, do you sort of have a vision for what the ideal system looks like? The electricity system in both regimes?
That's a good question, even though I thought about a similar version of that after a lot of the things that I learned today. I really think here our system is not very tidy. It's still very uncoordinated. So what I've learned over the last year really is that people that think about energy supply and those that think about load profiles, these are very distinct communities that don't overlap really right now. And there's no real clear champion, it seems like, here in the US or anywhere in the developed world who says, oh, we want to change our energy systems because we want to drive carbon emissions down, for example. And I think really the main players that are going to orchestrate that somehow are cities. Because I think a local utility just does what it does best to generate profits, right? So a lot of the solutions have to tunnel through certain barriers. There's no direct incentives for a utility to do that. But a lot of cities really want to have a high profile and show that they are able to reduce carbon emissions for various levels. And this is really what Eric and I think, are experiencing right now in Boston with the Boston Redevelopment Authority. Well, this is, of course, once you deal with city, it gets very messy because just there are many stakeholders that have to be satisfied, and it's a very complex process. And what we are trying right now here is at least providing the right amount of information so that we can say, let's put in the right incentives programs in place, let's flatten our load curves, and then supply PV and other assistance to it. So my ideal vision would be if cities really start owning that. They already have their GIS department. So what we basically promise to the city is your GIS department can create your load curves every year. You can do that yourself. And then you start planning how you want to shape your load profile. And then somewhat you work with your utility in bringing that down. And that, I think, will be necessary to address a lot of the technical questions when it comes to high penetration of solar that we saw before. Because if the subsidies stay, people are going to invest in photovoltaics. It's just going to happen right now. And then somebody will have to make sure that it still works.
So you're sort of envisioning a world in which load follows supply more than it does now. We have a supply following the load.
Yeah, where they at least talk to each other. That would be really wonderful. Okay. Or I think we should really look in terms of when we have incentive programs for buildings, we just tend to not consider the load curves at all, right? You pay somebody to solarize your home, or you pay somebody to winterize your home to make it tighter, so you change the infiltration rate. I think now we have the tools to actually see when you do that, what do you do to the overall load curves, and is that advantageous beyond the individual building?
So speaking of advantageous, Eric, you're talking about creating microgrids in a very different sense than we were talking about creating microgrids, where it's the primary means of electrification. Here you're providing an extra layer that allows renewables to be incorporated into an islanded system, sort of improves its resiliency. Does that create enough, it certainly adds cost, does it create enough value to justify doing it?
Well, I think that remains to be seen, but places like Goldman Sachs in Manhattan thought that it was a good idea because if you look at when you lose power, you also lose your ability to make money. And so they thought, well, we'll put a CHP plant in our basement, and which isn't actually that much money. I mean, in terms of dollars per kilowatt, it's not that much money. But the benefit that you get is that it's an 80% efficient system in the sense that you're using 80% of your natural gas. And so even some of that's going after your electrical load and some of that's going after your heat load. But your losses are much, much lower. And so you can offset your heating and your cooling using this type of system. And the question is, well, if you can do that, and a lot of places are doing that, what else can you add on to the system to make it a hybrid system? Can you add battery storage? Can you add PV? Can you add geothermal or other wind power? And make a large portfolio in this one type of grid. And then what can you do with that system that would be advantageous for the building or the community or the region that you can't do right now?
So it's a system analysis that you have to undertake on a sort of city-by-city basis.
And a lot of what Christoph has been doing is providing us with the building data. So we have data on electricity, gas use, heating, cooling, et cetera. And once we know those load curves per building, we can then go in and say, all right, we're going to pick a building, an anchor building that has a large thermal load, and we're going to start designing around that. Mm-hmm. And you can essentially radiate out from an anchor building and say, all right, we're going to pull all these buildings into the fold, and we know the load profile for all the buildings as a sum, and so then we can start designing basically small communities or little community microgrids. And so I think that's the movement that Boston is trying to start is going towards this decentralized national grid where you don't have huge, 5 gigawatt plants feeding 1,000 miles away some large city, you basically decouple those things. And I'm not sure exactly how much we can do here in Boston, whether or not we can do 100 CHP plants at 10 megawatts each, or one, but we're going to start down that road.
Okay, so we have something like 10 minutes left, I think, right? I mean, are there any questions formed in your minds? John? Just
what we try to do is, the hardest part of our work right now is, so we are working in 4 cities right now. We're modeling Kuwait City, Abu Dhabi, Riyadh, and Lisbon, and Boston. And the hardest part is getting energy data of individual households. And that still is, for us, really crucial, because we want to calibrate our models, obviously, to see that our models are right. And when you look at the literature, what you actually learn when you understand building energy use individual from a lot of buildings, you see all kinds of patterns of behavior come out. So one Central European study, for example, showed that in buildings that have really poor performance overall, because they're not well insulated and they're energy hogs, they're actually very often not energy hogs, because the people in there don't heat the whole building. They only heat the room that they are in, because they can't afford the higher costs. So the question of occupant behavior in buildings is one of the big unresolved riddles in all the research that we are doing. And we are trying right now to develop methods to basically, with statistics, model what the people do within buildings. And the more, I guess that links then to the randomized trials, the more individual building energy data we get, the better we will be getting at that. So I think this is a large part of what's just missing for us right now.
next question.
Hi, Cliff Ho with Sandia Labs. I also had a question for Christoph. I was interested in your map dwell software, but I wasn't quite clear. Is it accounting for building shading as the sun moves throughout the day and the year in terms of determining solar radiance? And are you also looking at the potential capacity of the PV in addition to just irradiance?
Yeah, so what the technology does, it uses LiDAR data. It builds this 3-dimensional model of a whole city. And some of the newer LiDAR data sets are so high quality that you see the trees very well. Then you need various algorithms to understand, is that a rooftop or is there a tree below it? And then we are doing very traditional high-end ray tracing, really, that for every hour of the year we are able to predict exactly, taking multiple reflections into account, how much radiation falls on a surface. We include also then aspects such as what's the temperature of the rooftop and how the efficiency drops down. So I can point you to the relevant literature. We get basically predictions for 2 rooftops in Cambridge within 5% of predicted annual electricity generated and what we were predicting for these rooftops.
Thanks.
Any further questions? I have a question for Christoph. What's a 2.5-dimensional view?
That's a term that we are using when you use LiDAR data. So LiDAR stands for light detection and ranging. Then you fly with an airplane over a city and you basically shoot shoot down with a laser and you collect a 3-dimensional point cloud of the city, and then you have really detailed geometry. This is typically not available, but what most cities have, they have shapefiles, so they know the floor plan of buildings and they know the height of the building. And so we just, we basically cheat. We assume every building is an extruded box, and that's called 2.5 dimensions.
Glad I asked. Question here. Sorry, I can't hear you. I don't know.
Do you think like distributed solar is good for like a dense populated city like Boston, or is it better for say a remote Indian like city? Yeah.
I would say that it's probably not great if you're downtown Boston, because the buildings are so tall and the amount of surface area you have on the top is very small relative to the volume, so the shape factor's wrong. But if you look at a place that's a neighborhood of maybe 3-story buildings like we have in Boston, in some parts of Boston, that is a better area for solar, definitely, because the shape factor is much better. But definitely, you can aggregate an area of solar power and then bring the lines in. So, Concord, Mass has a couple of 1 megawatt solar plants, and you could run lines. You could imagine running lines into Boston from there. But essentially using green space, I think utilizing green space is where we should start going. And certainly Lincoln Lab is doing that on their parking garage. And I think every parking garage in the entire country should have solar on top of it, because if you sit in your car in the middle of summer after it's been there for 5 hours, you know how hot it gets. And all of that can be captured and turned into electricity for not very much money.
Time for one more question.
I have a question. So you said that Boston is really pushing for microgrid. Is there actually a mechanism how to motivate people to put solar? So you mentioned that you put Prudential as the kind of the consuming tower,
Sure.
but you put the solar around. So how do you make people to put solar on their roofs?
Well, I think the city itself can incentivize people to do that. But I think largely the movement is to kind of start a dialogue between the utility companies, the city, the politicians in the city, and the people that live there. Because right now, as Christoph mentioned, there's a disconnect. So the utility folks don't want to hear that they're going to have less money because you're now adding distributed generation into their area of service. And so you have to basically say to them, all right, if we do this, you're not going to lose money, and here's how we're going to set up that structure. And then you have to talk to the politicians and say, well, this is a good idea because it's cheap, and we can serve a population that might be vulnerable, they might be old, they might have low income. And so the city is looking at doing that type of thing where they're going after low-income neighborhoods or vulnerable neighborhoods with solar power so that they can be empowered with that. Whether or not they can figure out kind of logistically or legally the mechanism to do that, I'm not sure. But I think starting this whole process is really where the city is shining.
Can I just ask, how does the utility play in the interaction there? Because if you take them out of the game, you're taking away their only profitable customers. I mean, you're sort of turning the normal paradigm of rural customers being more expensive to serve than urban customers, and making urban customers more expensive.
So the utility has what they call demand charges, which are what they would add on to a large customer. So if you have to pull in 10 megawatts of load for one building, then they're going to charge you extra for that. And so when you say, I'm going to put a CHP plant in the basement of this building, they don't like that because they're not going to get their demand charges. So there's a really delicate balance between what you want to do and what they want you to do and what's good to do. And so, it's a very interesting triangle there. And I think, like I said, the city's trying to figure that out.
Christoph, you were going to comment on that.
Yeah, I think we are just helping the city or individuals understanding opportunities. So right now, if you have a campus, if you look at most campus settings in Boston, they anyhow have district systems in place. Like MIT has that, Harvard has that, Mass General has that. So when you have a lot of buildings that are close together with different load profiles, you know that by connecting them together, you have an advantage. It's more here we try to, and owners know that because they own the building, so they have all the utility bills. They don't need what we are doing here, which is synthesizing the data. But by creating this on a really large level, you can basically understand these islands of groups of buildings of opportunities and say, here we really want to change something. And it would do thermodynamically, it would make sense to put you together, and you didn't know that maybe beforehand. And this is what we try to do here.
I think we've used up our available time. I'd just like to thank us for a nice session.